Good morning, everyone. This is Weijian Chen from Zhejiang University. My advisor is Shuibing. I'm honored to introduce our work, LeapGNN, a framework for accelerating distributed graph neural network training. This is a joint work with Washington State University. Unlike other neural network models, GNNs are specifically designed for training and inference on graph data. In our daily life, relationships between people or between people and products can all be abstracted into graphs. As a result, GNNs are widely used in recommendation systems, social network analysis, and other fields. Sampling-based GNN training is a standard approach for large-scale graph training. Let's quickly walk through the GNN training process with a simple example of vertex label prediction. The training data consists of two parts. First is the graph topology, which denotes connection between vertices and edges. Some vertices have labels, for example, representing user preference, while others does not. Additionally, each vertex has an embedding vector called a feature. A GNN model is a multi-layer neural network. For a two-layer GNN with a mini-batch size of 1, training starts by randomly picking one labeled vertex, say vertex 5. Then it does a two-hop sampling to create a subgraph. The worker then collects the features of the vertices in the subgraph. Both the subgraph topology and the gathered features are sent into the GNN model. Through forward and backward propagation, the GNN model parameters are updated. The trained GNN model can then be used to predict the unknown vertex labels. However, real-world graphs are often too large to fit into the memory of a single machine. Utilizing distributed memory across multiple machines is an effective solution. In this scenario, the graph topology is partitioned into two parts, red and blue. The red topology and its corresponding features are stored in server 0, and the blue part is stored in server 1. A small portion of the topology is redundantly stored to reduce sampling connection time. Let's illustrate a distributed training iteration and highlight the performance bottlenecks. Suppose the graph and the features are partitioned across two servers, marked in red and blue. The mini-batch size is 2, which means each server's worker randomly selects two labeled vertices for training. First, each worker generates a subgraph through a two-hop sampling. Then each worker collects the features of all vertices in its subgraph. If a vertex feature is stored locally, it is directly collected from the local machine. Otherwise, it is fetched from a remote machine. We use the bold circles around the vertex numbers to indicate the vertices whose features has been collected. Oh, sorry. Each worker's model then performs forward and backward propagation using its subgraph topology and collected features, followed by gradient synchronization and parameter updates. This completes one training iteration. We found that the process of fetching features from remote machine is the performance bottleneck of the entire training process. Tests on various datasets and GNN models show that this part of communication time accounts for more than 44%. Recent work has proposed many methods to alleviate this bottleneck, such as partitioning optimization, sampling more vertices from local server, or caching vertex features in GPU memory, and introducing new training schemes. However, all of them have some limitations. We refer to these methods as model-centric approaches because in their systems, when the model requires features that are located on remote machine, they fetch these features to the local machine. Next, we introduce our observation and design. We observed that in GNN, the amount of data fetched from the remote server is significantly larger than the model parameters themselves. Based on this observation, we are inspired to leverage model migration to reduce the amount of data transfers during GNN training. Our goal is to move the model to the servers where the vertex features are located, rather than fetching features from remote servers. We call this the naive model migration method. Let's use the same example to illustrate the naive model migration method. Let's first focus on the computation of one model. The model 0 is still assigned to be trained using vertex 6 and 3. So the worker first generates subgraph 0 through sampling. Then model 0 collects the features of vertices in the first layer of subgraph that are stored locally and performs partial forward computation. We label these vertices as red circles. Next, model 0 and its intermediate result migrate to server 1, where it collects the features of blue vertices and completes the forward computation of the first layer. Finally, model 0 and its intermediate data migrate back to server 0 to complete the forward computation of the second layer and the entire model backward propagation. These two models move alternatively between the two machines and perform computations in parallel. After forward and backward propagations of both models are completed, the gradients are synchronized and the parameters are updated at the end. Compared to the existing model-centric methods, the naive model migration method completely eliminates feature data transmission between two machines. However, this naive model migration method is only more efficient than the original method in some cases, but not in others. This is mainly because naive model migration introduces intermediate data transmission, which are needed by backpropagation. Therefore, we need to further improve the naive model migration. First, we noticed that when the sampled subgraph is divided into smaller subgraphs, data locality can be improved. Specifically, we first define the micrograph as a special subgraph with only one root vertex. For example, subgraph 0, sampled from mini-batch 6 and 3, comprises micrograph 6 and micrograph 3. We noticed that most vertex features in the micrograph are on the same machine where the root vertex is located. For example, in the micrograph 6, most of the vertices features are on the same machine as the root vertex 6, which is why they are all in red. We found that the locality of micrograph is always higher than that of subgraph using various graph partitioning algorithms, sampling algorithms, number of sampling layers, or number of servers. We believe this is because GNN partitioning algorithms tend to place adjacent vertices on the same machine. Based on the enhanced locality of the micrograph, we propose the micrograph-based GNN training. Let's focus on one of the model 0. Compared to naive model migration, there are two key differences. First, the forward and backward propagations of one micrograph are completed on the single machine. For example, micrograph 6 is only used for training on server 0, and micrograph 3 is only used for training on server 1. The advantage of this is that after the backward propagation is completed, all intermediate data except gradients are released. This avoids the overhead of transferring large amount of intermediate data in the naive model migration. Second, it allows the fetching features of vertices that are not locally in the micrograph from remote servers. Note that only a small number of features need to be fetched from remote due to the enhanced locality of the micrograph we mentioned before. Overall, it combines model migration with the locality of micrograph to reduce the amount of data transferred across servers. At the same time, Model 1 follows a similar process, but on the other machine. After both models complete training, gradients are synchronized and model parameters are updated. Moreover, since this method does not change the random assignment of training vertices and the training process for each model, it maintains model accuracy. Furthermore, we made two additional improvements. First, we found that feature transmission between different time steps on the same server is redundant. For example, the features of vertex 1 and 4 are fetched twice. Therefore, we designed a vertex feature pre-gathering technique to reduce the redundant transmission. The key idea is to proactively check which vertices will be needed in the next few time steps and fetch the features of multiple vertices from remote together, thereby reducing redundant feature requests. Second, when the cluster scale is large, an iteration involves more time-step computation and synchronization, leading to increased time overhead. For example, 3 servers requires 3 time steps to complete one iteration training, as shown in Figure A. To address this, we propose micrograph merging technique, which reduces the synchronization time overhead between time steps by merging some groups of micrographs. After merging, an iteration of training requires only 2 time steps, as shown in Figure B. 2 questions arises: which micrograph should be merged, and how many micrographs should be merged? We designed a simple greedy algorithm to solve these questions. For more details, please refer to our paper. Our experiments were conducted on 4 servers with a single 800 GPU. We selected 5 popular GNN models with various hidden sizes and number of layers, and 5 datasets of different sizes. We compare LeapGNN with DGL, P-Cube, and neutral star in terms of performance. Additionally, we compare LeapGNN with the naive model migration method to demonstrate the effectiveness of our optimization. The experimental results show that under both mini-batch training and full-batch training, LeapGNN outperforms other systems by 1.1 times to 4.8 times across various datasets and models. Moreover, we sequentially enable each technique, and the results show that each technique further accelerated distributed GNN training. Here are more details. The first technique significantly reduced the local miss rate of features. The second technique minimized redundant feature requests. And the third technique adaptively adjusted the number of time steps in an iteration, automatically balancing performance improvement and additional overhead. Additionally, we tested LeapGNN by varying feature dimensions, batch sizes, fan-out sizes in sampling, and the number of distributed servers. The results show that LeapGNN consistently outperformed the alternatives. For more evaluation results, please check out our paper. In summary, we identified the problem that feature transmission has become the bottleneck in distributed GNN training. To address this, we introduced a feature-centric model migration approach to reduce the amount of feature transmission. To make it truly effective, we developed 3 key techniques, including micrograph-based GNN training, vertex feature pre-gathering, and micrograph merging. These innovations enable LeapGNN to achieve up to a 4.2 times speedup compared to a state-of-the-art counterpart, P-Cube. We have open sourced our code and successfully passed the artifact evaluation. Thank you for your attention. I'd be happy to take any questions and comments.